Welcome everyone to the BS and Beer Show, BS for Building Science. Tonight we are going to talk about kitchen ventilation, which is really exciting. We have a special night tonight as NESEA After Hours, so hopefully a lot of you are enjoying the NESEA conference and joining us for their After Hours event tonight and BS and Beer as a group together. Tonight, I am actually, you'll all be really proud, drinking a sour beer. This one goes out to you, Dan. I actually like this one. So he wins the sour beer competition because this is the first sour I've ever liked. So I think he homebrewed it himself, if I remember correctly. If he didn't, he sent me one that he likes. So if you're on, Dan, put it in the chat box. But tonight I'm drinking a sour beer sent to me courtesy of Rockwool Dan Edelman. We also started this BS and Beer show based off of our local groups. So we like to encourage local groups. If you go to the bsandbeershow.com, there are a bunch of local groups mentioned. If your group isn't on the page you want it to be, send us an email, let us know. And start your own group. There's a little link on there for some topic ideas and other things that we've used to start our own groups in our local areas. So that was how this got started. If you're not already on our mailing list, go to the bsandbeershow.com and get on the mailing list. You'll get a weekly reminder of what the show topic is that week and a reminder to show up for the live events. Also, the shows are posted afterwards on Green Building Advisor and our YouTube channel. So if you happen to miss out or you want to check out past episodes, we've had a bunch of great episodes previously that are all available on YouTube. And I want to say a special thank you to Green Building Advisor and Fine Home Building for being our media partners, and tonight to NESEA for joining us at NESEA After Hours. So I'm going to turn it over to Brian to do the mechanics of the show. So off to you, Brian.
Yeah, thanks, Emily. Hey, everyone. Brian Pontalillo from Fine Home Building and Green Building Advisor, and also excited to be working with NESEA tonight on this episode and of the show. So glad maybe we'll have some new people in attendance, and we'll have an interesting segment of the show later on. In a few minutes, we'll turn it over to the panelists for some presentations on our topic, kitchen ventilation, and after the presentations, we'll move on to group discussion and questions from anyone in attendance. And then, as I mentioned earlier, tonight we're going to go to a sort of free-form discussion towards the end of the show. So if you're in attendance, and I don't remember how we decided that we're going to do this, but I think if you're in attendance, you're going to get your video is going to get turned on. So when we go to that portion of the show tonight, you will be on the screen. So if you don't want to be on the screen, or if you don't have pants on, get prepared, because you will be on screen later on. So I think that's it for me for tonight, and I think I'm handing it off to Travis.
Hey, I'll just say hello, and then it's on to Mike right away to introduce our panelists. I know that it's very important to my friend Jake that I introduce Ben Bogey as Ben Boogie. So now that that's out of the way, I'm drinking a Lef, which is a delicious blonde, and I am going to kick it off to Mike to introduce our panelists. Thanks for joining us.
Thanks, Travis. I'm Mike Maines. Tonight I am drinking a sour also. The BS and Beer show started as BS and Beer, a local discussion group at our local microbrewery, Lake St. George Brewing. So I am drinking their blueberry sour made with local Maine blueberries. It's a nice tasting beer. Tonight I have the honor of introducing our guests. Kyle Macht is a principal at Macht Architecture along with his dad, Paul Macht. Kyle studied architectural engineering at Penn State and worked as an energy consultant before moving into residential design and project management. Macht Architecture designs homes that have a strong connection to the site, that are aesthetically stunning, and that perform at very high levels, up to including passive house performance. On more of a personal note, Kyle and I, as somebody mentioned earlier, Kyle and I met at the 2016 Fine Home Building house called the Pro Home at the time, that I designed and Mike Burton built down in Rhode Island. And this is actually, so there's a Fine Home Building connection, and for the NESEA connection, this is actually the first year since then that Kyle and I have not met up for lunch at the annual NESEA conference. So Kyle, it's good to see you here tonight.
See you too.
Can you tell us what you're drinking tonight, if anything, and is there anything I missed that you'd like to add?
So I am drinking a golden milk, which is sort of steamed milk with turmeric and ginger. And I'm drinking it out of the Ultra Air Yeti mug that you guys sent me for answering a question correctly. So I guess that's about it. I have kids in the back, so you might hear them from time to time, but I think you covered all the points.
Okay,
Also, I guess one little thing, a big part of my history and education in school had much more to do with solar decathlon than the architectural engineering that I was focused on. Solar decathlon was about 5 years of my life. And Ross has a similar story to share there. But anyway.
Excellent. Ben Bogie is a second-generation high-performance builder. His career has encompassed work ranging from historical conservation of early 18th century homes, building cutting-edge net zero and passive house structures, and high-end interior millwork and finishes. Ben is a regular contributor to a number of industry publications and websites. He teaches high-performance best practices at JLC Live, the Remodeling Show, and the International Builders Show. I've noticed that a lot of builders of high-performance homes start out as finished carpenters and cabinet makers, and but now building to high levels of performance is kind of the new craftsmanship. I don't know many people as articulate as Ben on craftsmanship of all types. He's as knowledgeable about high-end millwork and tools as he is on subjects like ventilation and mechanical design. And a little known fact, Ben is an avid mushroom hunter, so you could say he's a fun guy. Sorry, that was,
that was a stretch, Mike.
I know. It kind of hurt to say, but Ben, what is your beverage tonight, and would you like to add anything?
All right, so I'm this evening drinking, if it'll pick it up, Lone Pine Slush Punch, which is a imperial double fruited sour ale. So sours are the thing tonight. This is from my favorite brewery in Portland, which is Lone Pine Brewing. Yeah, happy to be here. Happy to be on BS and Beer again. Steve Basic, if you're listening, thanks for the Ben Boogie. That's everybody out there. It's Steve Basic Steve, instead of Steve Basic. Let's just get that clear. And happy to be part of the conversation tonight.
All right. And last but not least, Ross Chathui founded TE2 Engineering in 2010 and has been a regular presence on This Old House and Ask This Old House since 2011, where he is their resident expert on home technology and renewable energy. I grew up watching Ross's dad, Richard Chathui, on This Old House, and his grandfather was the plumbing and HVAC expert on the very first season, which puts Ross in the unique position of being a third-generation This Old Houser. I don't know if anybody else has that distinction. His company focuses on high-performance HVAC design, renewable energy design, and integrated smart home design. And it's also interesting to note that all three of our guests followed in their father's footsteps when choosing a career. That may be a first here. Ross and I had not met before tonight, so although I have seen him on TV, and I was looking for a personal connection, and I found it that we are both graduates of Tufts University in Somerville, Mass.
All right, Jumbos.
Jumbo, go Jumbos. Ross, is there anything else you would like to add, and can you tell us what you're drinking tonight?
No, I think you nailed it. But I'm drinking, I don't know if it'll pick it up, but just a Harpoon Rec League IPA. I don't know why it's not working. There we go. Maybe there we go. But yeah, happy to be here. Thanks for the invite and excited to talk kitchen ventilation.
Excellent. Thanks for joining us. Yeah, I guess you guys have Kyle, I think, has a presentation, or somebody has a presentation.
I'm in charge.
You're in charge. Okay, if you want to go ahead and share your screen. And
all right. So we're here to talk about kitchen exhaust today. And so we're each going to take turns going through this a little bit. We felt it was unfair for one of us to dominate the conversation. We're trying to make this quick and sweet so that we can get into a lot of discussion, because I'm sure there's going to be things to debate. So first, I'm going to cover particulates and cooking and what that's all about. So there's obviously huge conversations about carbon emissions, as well as off-gassing from cooking with gas or propane. And so you can see there's a lot of things that you could off-gas there. One of the most notable is the NOx, all the nitrogen-based elements. And so there's some severe health impacts that we're going to get into. From an electric standpoint, with the electric resistance coils or an electric surface element, which isn't quite as bad, there's still electric ultrafine particles and NOx that's emitted. from an induction cooktop standpoint, that's even lower in terms of emissions from the ultrafine particles. And then when you're cooking the food is also, while it's being cooked, off-gassing quite a slew of different things. All that being said, the goal is to be cautious of our health. So looking at some of the EPA's standards in terms of NOx, because that's, and especially nitrogen dioxide here, the parts per million or parts per billion should be below 100 for the outdoors and below 100 for the indoors for an hour of exposure for a human occupant. And so you can see at the bottom of this image, this is from Rocky Mountain Institute, who's done some really cool studies on this. But almost most of the cooking that you're doing, whether it's from the cooktop or the oven or potentially a toaster oven, are giving more emissions than what those guidelines are. So if you don't ventilate, you can really run into some serious health issues. And the most critical of these health effects from nitrogen dioxide have to do with the younger generation, the kids. So I've got a 4 and a 6-year-old back behind me here. And so there's some serious health concerns with their intake of all of these harmful particles. So it's not just the cooktop, and that's something that we need to be really specific here. It's the toaster, it's anything with an electric element or gas or something burning that is off-gassing all these particles. So candles, a fireplace, whatever type of fuel it is, unless it's electric. But all of these are off-gassing a bunch of these different particles. And so looking at the ultrafine particles, that's something that tends to be talked about quite a lot because it's pretty serious and it's something we don't see. So you can see the thickness of a human hair is 50 to 70 microns there. That's a grain of sand on the bottom left. And so PM10, 10 microns or smaller, you can see is about a fifth of the width of a human hair. And then PM 2.5 is even smaller than that. And then there's particles that are much smaller than that. And those tend to just go straight into your bloodstream. And so I think one of the most interesting things during the research that I did to make sure I was up to speed, I didn't realize how often people were using their ventilation system for their kitchen. And so part of that is for different reasons. So 21% in a study that was done don't actually have any fan at all. 10% don't use it. 32% use it infrequently or only when needed. Who's defining that only when needed? The homeowner. So only 13% use it most of the time when the oven and the cooktop is used. I'm sure many people, less than that, are using it when the toaster is used as well. So basically, barely anybody is using ventilation appropriately. And that's assuming that the system's even designed correctly to begin with. And so in terms of design, I'm going to drop it off to Ross here.
Cool. So what do we do about it, right? We know that, kitchen can be harmful to our health, and it can be harmful to the indoor air quality. So one of the ways that's typically solved is with kitchen range exhaust. So, it's a problem though, because when you're talking about large cooking surfaces, when you're talking about 36-inch range, 48-inch range, 5-foot ranges, these things are big, which means they need a large amount of airflow. And then, the other challenge is we can't tie them into an ERV or HRV, right? So that's one of the common kind of misconceptions. A lot of people say, oh, I could tie the range right into my ERV or HRV. And that's really not the case. You got grease, you got high temperature, you got a lot of other, issues that an ERV or HRV can't handle. It's not really designed for. And I put some typical, exhaust rates up here, and it really depends on the manufacturer and the type of cooking that you're doing, whether it's on a gas or induction, for example. There's going to be different rates. Typically, depending on which research, or scientific data you're following, it's going to be somewhere between 100 and 300 CFM per foot of cooking surface. So if you got a 36-inch range, that's a 3-foot range. You're going to be somewhere between 300 and 600 is what's going to be recommended by most manufacturers for that type of cooking surface. So we can keep going. So how do we deal with it? There's a lot of different ways that kitchen range exhausts are done. We try to highlight them, the ones we see the most. We'll start off with what I would be, consider to be the best way to do it, and that's with a correctly sized wall canopy hood. So if you look on the left-hand side of the screen, you can see a correctly sized hood is one that covers the full cooking surface, comes out to the front, over the front burners on the cooktop. And it's obviously venting at the right rate. There's other ways you can go undersized canopies, which cover just the back burners. You can do recirculating. You can do just a ceiling exhaust. The island range hood is sometimes common, downdrafts and pop-up downdrafts. So these are all ways that it's done. Some are far more effective than others. I would just, like to say that really the only way that, we see it as a functional way of really capturing the contaminants off the cooking surface is with a correctly sized correctly sized kitchen hood. You need that kitchen hood to be correctly sized. It needs to be, rule of thumb is at least the square footage coverage rate of the cooking surface, and the deeper, the better. So the deeper the volume of the hood, the better capture efficiency it's going to have. So we can keep going. So what happens when you have a very tight building and you're exhausting a lot of air through a tight building? You run into a problem. How do you solve it? That's called makeup air. I would define it as air intentionally brought from into the building from outside. That's basically going to replace the air that's exhausted, and it's going to be code in a lot of areas across the United States. What we're trying to do is we're trying to deliver safety and prevent backdrafting of appliances. So we want to make sure the air quality is nice and healthy, and we don't have backdrafting of fireplaces, gas, oil, any type of furnace or boiler, any kind of combustion device really that's not sealed combustion is at risk for backdrafting. Dryers are a common one as well. So next slide. So how do we deal with makeup air? Typically, you see three different methods being used. One is mechanical ventilation. That's with an active fan that brings in the outside air. Another option is passive ventilation, which is typically done by a motorized damper, which is interlocked. And then the third option, which is a fixed louver or just an open window, open door concept, which may not meet code, obviously. But and I've just grabbed a diagram from one of the manufacturers on one way that it's done in the cold climates. And that's obviously fresh air being brought in through a motorized damper, through an insulated connector, because this could condense, filter it, put it through a fan, put it through a heater, and deliver it back to the space. That's a common way that it's done as well. So where do you bring the makeup air? You see it all over the map in terms of ways that it's brought into a building. You could bring it into the return of the air handler that's feeding the kitchen. That's in the left-hand side there. You could bring it in behind the cooking surface or underneath the cooking surface. There's some potential issues with that, but that's one way that's done. You could bring it into the ceiling. You could bring it in through the cooktop or underneath the fridge, even in the toe kick. So there's a variety of different ways that you can really bring the air into the kitchen. Some are more effective than others. The devil's in the details. So it's, one example is if you start to bring the air in behind the cooking surface, the challenge there is if it's coming in at too high of a velocity, you get a phenomenon called spillage. Basically, you're not going to be capturing the contaminants through your hood because there's air blowing on the cooking surface, which is going to make it, migrate into the room, and you're not going to, not capture it. So there's also aesthetic challenges. How do you bring the air up behind the cooking surface? So just to, give you a highlight on some different ways, and we'll get into more of this, I think, in the conversation. Here's one way that we did it on a recent project. This is called the hood within the hood concept. So outside air is coming in the blue, and exhaust is leaving up through the backside of it. And you can see we're getting no spillage. We're getting proper capture of all the smoke off the cooking surface, and that's most important. So the only thing I'll mention here is that this type of solution may not be the best fit in a really tight building. So we have to be sensitive about the air tightness of the building. And also I'll mention that the closer you bring the makeup air to the cooking surface, the higher the risk is for spillage and not getting caught, proper entrainment and proper capture of the contaminants. So when it's done right, well executed, it's a great way to go. This is a very busy chart. And what it's trying to highlight is how easily it might be to depressurize your house in backdraft appliances or fireplaces. So I'm going to try to take you through it as quickly as I can here. So if you think about there's tight, moderate, and leaky construction. So that's defined by a blower door reading. So if you look at the x-axis there, it's from 1,000 to 1,500, or sorry, yeah, 5,000. And that's CFM at 50 pascals. If we look at the black solid line vertically that's traveling up and down on the page, that 2,500 number corresponds to a house that's 2,500 square feet that has 7 air changes at 50 pascals. So to break that down that's code in most areas. If you look at the 400 CFM exhaust requirement on the vertical axis, that's the black line, you can see where they meet. Anytime that you're going to have an exhaust rate higher than 400, even in a 7 ACH 50 house, you have a risk of backdrafting. So if I had a 600 CFM hood without makeup air, I'm going to most likely, I'm going to backdraft, gas-fired appliances, oil-fired appliances, and fireplaces in that kind of configuration. So it's a nice chart to get a feel for, based on your air tightness of your building, how risky are you going to be without having makeup air to offset the pressure differential that might be generated in your house when you run your kitchen exhaust fan. So, the common solution that people always tell me is, it doesn't matter. I have an ERV, right? I have an HRV or an ERV. That's going to solve it, right? That's my makeup air. And that's not actually the right way to think about it. ERVs or HRVs are balanced ventilation machines, right? They bring the same amount of air out of the building as you bring into the building. So if I have 100 CFM ERV, it's bringing 100 CFM out, bringing 100 CFM in. It's balanced, meaning it has no effect on the pressure of the building. It's neutral pressure. If I run a 600 CFM kitchen exhaust fan, the ERV is not going to do anything realistically to help me with that negative pressure in that building. So you need makeup air to offset the kitchen range exhaust, especially with 600 CFM in this example. So ERV is not going to solve you there. ERVs are great, huge fan. It's great for ventilation, whole house. It's great for indoor air quality. I know you guys have talked at length about that, but that's that. So let's keep going. I don't know how we're doing on time. I get often asked, how do you do a makeup air system on the cheap? So the most cheap way that you can typically see it done is a motorized damper interlocked on the kitchen exhaust fan. So basically, kitchen range becomes active by a CT clamp. It triggers a motorized damper to open that lets outside air flow into the return of your air handler. And that's a common way to do it. It's not the best way to do it, but it is a way that meets code, and it's pretty simple and cost effective. I would say it's better than nothing.
We're ready for you, Ben.
Okay, so I think Kyle and Ross have really kind of set up good. I'm the humble carpenter in the group here, so I'm going to just run you through some quick photos that I had on my phone to show you what a typical install for me looks like on one of our projects. So what you see here amongst the job site messes is a 3¼ by 10 duct that's coming down and being terminated right behind where the range sits, as low as I can get it. And we can discuss a little bit more on strategy as we move further through the conversation here this evening. But what I really want to highlight is that I'm really trying to control where I'm delivering the air. I've gone through a number of different methods of where I bring the makeup air into the project. We've done the behind the refrigerator thing because we figured that the refrigerator coil heat kind of tempers the air a little bit. We've brought them in through the air handler units. I've brought them in through the toe kicks. I've actually poured them into semi-conditioned basements to help temper the air. And through playing with all these methods, the one that I've settled on for us is, kind of a real world approach to what's actually going to get installed in the building is bringing in just a simple duct to come right up behind the range. And what that is going to do is that's going to cause something that Ross touched on, and that's going to be entrainment. So what's going to happen is this air is going to flow out of this 3¼ by 10 duct right underneath the range, and it's going to spill up around the range from the bottom, and it's going to create a negative pressure situation as it passes the cooking surface, and it's going to be pulling all of that exterior air up and into the flow path of the hood on its way up. So critical things here. I am not a fan of flexible ducting. I try and avoid it as much as humanly possible. I think it's just it's a cheat. Sorry, no offense to anybody here that's big on the flex duct train. So 3¼ by 10, solid ducting. fully masticed on its way up. And you can go to the next slide here. I'll show you where we transition from. Okay, so now I'm going to go right back on the words I just said a moment ago, and I'm transitioning to flex here, but it's for a reason. So what you're looking at here is this is transitioning up through my ceiling, and this is our OSB air control layer in our ceiling here. We use a rigid air control layer, and we can dive into that some other time. But you can see that 3 1/4 by 10 coming up here, and it's transitioning to flex for about 3 feet right here. And it's all well sealed. You know, this is critical. Make sure all your ductwork is sealed. The reason it goes to flex is because I want to try and break the thermal conductivity between the metal duct in an unconditioned space and the metal duct inside of the conditioned space, trying to limit the amount of any potential condensation risk that can happen. So it goes up into a 3-foot section of flex right here, and then travels its way up. Next slide. Next slide. Okay, so now we're going up here. This is a remote blower situation. We go up to a remote blower hung on some cheap vibration isolation dampers. All of this, like you can see here, this is the exhaust coming up for the hood. You can see right in the background, you can see the makeup air coming up. Everything rigid pipe as much as possible. Everything will be fully masticed at the end of the job. I really like remote blowers whenever possible because I feel that you get better performance out of them, number one. And number two, we can take the noise outside of the building. We can go with vibration dampeners here. We're isolated by the flex duct and all of the rigid metal, so we're not getting a vibration transfer down into the house. One thing to note is the 8-inch round that you see there, that's actually the hood exhaust. That doesn't go through plastic flex, that goes through aluminum flex. I don't want any plastic whatsoever in the airstream of heated exhaust air. Just, I think it's bad practice. I think it'll break down as it gets grease and particulates and stuff on it over time. So we can go to the next slide. This goes up here, and this is just a basic off-the-shelf 6-inch motorized damper. We do a number of different approaches. Like Ross said before, I use CT clamps sometimes to sense the current when the hood comes on. I've used pressure switches in the past. And in this case, because the way the remote blower is set up, I actually just have a circuit that comes right off of the same line as the remote blower, powering a 24-volt transformer that activates the 6-inch damper, bringing in fresh air. We are going to dive in a little bit more into some other strategies, higher end ways to do this. Those are great approaches, but what I'm seeing is most people out here in the industry are not installing makeup air at all. So sometimes it's a hard push for us to go with a really great system. So this is a very effective step up that's pretty cost palatable for most builders to achieve. Additional parts costs here beyond what's normally associated with the range hood is maybe $100, $150 plus a little bit of labor time. So there's really no reason not to do it. And that's the end for me. Oh, I'm sorry here. One more thing. So this is terrible dirty shot, but I had it on my phone right here. You can see the makeup air coming in right there behind where the range will sit, behind where the broom's sitting right there. And something like Ross touched on before is I really want to make sure that we have a properly sized hood. So I want that hood to come all the way out, at least to the front of the cooking surface. And I like it to extend past on the sides as much as we can possibly get. If you look at commercial codes for, commercial kitchen setups, they usually have to extend, and Ross probably knows this off the top of his head, but it's like 18 inches to 2 feet plus out in any direction from the sides of the cooking surface and the front of the cooking surface in order to make sure we get capture. That's a hard sell in residential, but this is about as best as we can get.
So we have a bunch of resources here from all three of us, and there's more out there too, but some of these we got some of the information from, but also these are great resources for everybody to go through in terms of indoor air quality mostly, and some other building science related stuff too. And for those who haven't been part of building science and beer before, this is all recorded, so you'll be able to see this whole presentation as well as all of these links later in the future. And that concludes the presentation.
Awesome. Thanks, guys. I'm really hoping, Brian and Travis, that you guys have been following all of the chatter in the chat box to follow up on that. Do you have a list of questions that you picked up there?
There's been a ton of stuff about the high CFM demand. 600 CFM, I believe is in the code, is the tipping point for the for the makeup air requirement. Oh, it's 4? Thank you.
Yep.
My mistake. Anyway, the requirements, or excuse me, the implications of that for most people that don't have a super airtight house, or even those that do, are pretty broad, as you kind of talked about. And I think for the entry level builder, it's a huge, like, oh God, what are we going to do about this makeup air? This is really complicated. So your bare bones or economy approach, I can't remember the proper verbiage that you gave it for the lower end. The economic approach, I think, is what you said. I've done that approach, and it's fine. And I didn't have any problems with it. It's just not going to perform the way that the house could in a well-built system. The better approaches you described are obviously better. It's just that so many folks are putting in these giant ranges and massive commercial kitchens to almost never cook at home. You know, they use that for the holidays or whatever. And I think a lot of questions about that CFM requirement circle around that. So I think you could condense that one into several, or those several into one, rather.
Yeah. I think it's important also for everybody that's listening to understand that requirement should not be our requirement for good design. Our requirement for good design for any type of levels of air being pushed out should be matched, balanced with air coming in. So even though 400 is the code, I would argue that any amount that you're exhausting needs to be brought in through a makeup air system, regardless of the cost affordability standpoint of the home. If they can't afford to do that, it shouldn't be building the house, in my opinion.
And just something I'll shoot back, if people are actually worried about these flow rates coming through the building, I have the bad habit of testing any of these installed systems after I've done them. And some of you may have heard me talk about this before. I've installed 1100 CFM downdraft systems, you know, from good reputable manufacturers, and done them in proper, like, well installed typical layouts with all rigid pipe, and measured about 250 or 260 CFM actual discharge. So, and that was not in an overly tight building. That was like a 1.8 ACH 50 building. So tight, but not obscenely tight. And even after adding makeup air, I was still only getting 300 and change out of it. So what I'm diving at here is to be cautious about how effective these blowers are that you're actually installing. You know, obviously downdrafts have a number of limitations going against them from the outset, but we're talking about people's health here. We're talking about people's safety. We're talking about potentially being in buildings with, you know, medically compromised or immunocompromised or, you know, respiratorily compromised people, or possibly creating those effects in people if we don't take this stuff seriously. Just because we haven't been doing it doesn't mean we should just brush it off. I think it's our due diligence to try and pay as much attention to this as we can. Are we going to hit it right out of the park the first time? No, but we need to be paying attention to this and at least trying.
I think that I was going to say that brings up a good question too that I saw pop up in the chat box at least once, which is, you know, the passive house idea that if you don't have a gas range and you have an electric and you have a recirculating hood. Exactly. So you're all shaking your head. Yeah. You're all shaking your head no. And so, you know, several people or at least had talked about that. And you know, I think you touched on it a little bit, Kyle, in the beginning, stuff that comes off an electric range where everybody thinks that, like, oh, the electric range is fairly safe. But
my favorite article and story that I heard about that came from Jod Straub through Allison Bales. If you don't follow Allison Bales on Energy Vanguard, it's a great blog that you can read. But the article is basically named something like, why do a recirculating range hood? Would you do a recirculating toilet? And that's essentially what you're doing. You're capturing major grease, but you're still pumping all of those small fine particles, ultrafine particles, all the other contaminants that those grease capture units aren't catching, and throwing it all around the room instead of where it needs to be exhausted. So right. In my opinion, and I haven't seen the exact data on this, but most of the time it should be doing more harm than it is helping, except in extreme scenarios. But from a passive house standpoint, I would argue absolutely not. Do you want to do that? You really want to do a balanced ventilation system for the house and a balanced ventilation system for the cooking, and theoretically balanced ventilation system for anything that you might be exhausting air out of the home for.
Let's be clear here. We're not just talking, this is not just about gas-fired or combustion-fired cooking. It's literally the stuff that comes off of your food as you cook. You know, when we superheat oils in our pans, we're creating acreolin, which then polymerizes and mixes with numbers of different chemicals in the building. These things that are coming off during cooking are then reacting with our household cleaners, our paints, our finishes, our furniture in the building, and creating all sorts of really noxious and really kind of terrible byproducts. And it's tough to really call a lot of this stuff out right now because the research is really so young right now. But the
big one that you should never clean with while cooking is bleach. That's the one that creates some really scary side effects, especially with cooking oil and bleach at the same time.
Yeah. I think it's just important to outline that, you know, to follow up on both of those points. It's not just gas ranges, right? Everyone thinks, oh, I put an induction cooktop in, I don't have the same risks. And you don't have the combustion byproducts with an induction cooktop, but you still have plenty of harmful contaminants coming off the cooking surface. Cooking is a harmful activity, right? It's harmful to our health. Using the oven is harmful to our health, right? If I run the oven in my house, my FUBA, particularly, my PM 2.5 spikes, elevates, goes through the roof, right? So the proof is in the sensors and the data that we're measuring that, these activities are harmful. So you got to have balanced ventilation across the board, regardless of whether it's an induction cooktop, whether it's an oven, whether it's a kitchen range that's gas with 6 burners and a charbroiler.
What's kind of nuts, what also applies to that is toasters, hair dryers, anything with electric resistance heating element is producing ultrafine particles while it's burning. Because whatever dust or anything that lands on that heating element gets burned off and then it's spread throughout the house.
Right. Yeah, and I think another key point is to hit upon is that from a sound perspective, Ben mentioned remote fans. Huge fan. I think that's a great way to do it. And so if we can remove the fan, sound noise from the actual, the typical hood, the fan that's inside the hood, if we can remove that noise and move it elsewhere, people are going to be more apt to use their kitchen exhaust fans. I can't tell you how many people tell me every single time I turn on my kitchen exhaust fan, it sounds like a train going by or whatnot. And I think we all have experiences with seeing that. And so, it has to provide a noise comfort to the house, as well as a thermal comfort to the house. So if either one of those are compromised, people are going to choose not to use it because if you can't see it, you can't smell it. If you're not measuring it, you don't know it's there. Right. So it's super important that we design these systems to be effective, but also that they work, well, that they're not going to create, comfort issues or noise issues, et cetera.
Two pushbacks that I often hear about kind of the method that I employ for makeup areas is number one, that there's going to be an energy penalty from bringing in untempered air into the building. And yes, that's absolutely true. And my response to that is number one, it's people's health. Like I said, we're dealing with here, energy is always going to be secondary in my hierarchy to people's health in the building. And number two is if we're bringing in, untempered air into a building with a highly efficient heating system in it, your cost to reheat that air is going to be comparatively low. Are we worrying about what the numbers on our spreadsheet at the end of the year say about the building's performance, or are we worrying about taking care of the quality of the air inside of the building? The other one that I hear pushed back a lot on is if I'm bringing untempered air in near the cooking surface, that the clients are going to be unhappy because there's going to be drafts. I've done this, I can't even tell you how many times, and I've yet to have one client come to me and say, hey, can we shut off that makeup air because I've got cold drafts across my toes. So I feel like that's just like a myth that's been circulated about these systems that, sure, probably it does exist, but it's not nearly as common as people like to say it is.
Just to talk on the positive side here real quick, there's a lot in the chat about, let's just stop cooking. Let's forget about it. Let's do sushi. And all of this, if we do the design right and get the capture efficiency correctly, make up air correctly, this can perform beautifully. And all the off-gassing, at least almost the majority of it, can be evacuated correctly. So as long as it's executed correctly, things should be fine. It's just not executed correctly very often, which is the challenge of why this is and why we're having this conversation tonight.
Right. And also the risk is higher as you build tighter, right? If the trend across the community is to build tighter and tighter houses and get to pass oil standards or anything even close to that, the air quality inside the building doesn't move to outside. It doesn't leak, right? So we have to breathe for the occupants of the building. And so that makes kitchen ventilation that much more important. It makes makeup air obviously that much more important.
Yeah. And I think there were a couple of things that came up in relation to that in the chat, which was, have any of you ever done any preheating of the makeup air, preconditioning of the makeup air? And also, in addition to that, you mentioned comfort and noise level is, and I don't know if you have manufacturers, but what do you aim for as far as zones go when you're talking about sound? We've had some where we have bigger systems and they pull the fan out farther into the ductwork. And is that as effective, and is it quieter than having it at the source?
Yeah. So as far as the fan location, the loudest fan location is going to be inside, the one they call integral to the hood, right? Where the fan's inside the hood itself. That's going to be the loudest by far. There are some that are quieter, especially the variable speed units. We just used one on a project that was made by Best, which I think is a sub of I think Brown or Brown Newtone. So they've got an ECM blower that's variable speed. That's a nicer unit than the typical one that you see. But it's still, when it goes to high speed, it's noisy, right? And it's still going to make quite a bit of noise. The inline fans, the remote fans that Ben showed in his photos there, those are going to be far, far superior in terms of noise level. You're moving the motorized impeller outside, away from the hood. You're moving it down the duct stream. You're moving it close to the exterior termination of the building. Far better. And in that category, you have three different styles of fans. You've got centrifugal, you've got mixed flow, and you've got axial. The sweet spot in my experience is a mixed flow fan. That would be like a Fantech FKD fan, or a Solar and Palau TD fan, or something like that, which is a nice unit for mixed flows. Are great at decent static pressure and decent CFM. If you go with a centrifugal fan, they're really, really good against static pressure. So if you have a really long duct run till you get to your outside wall and you got really tight on your duct sizing, you're gonna probably need to go centrifugal. So it really depends on the application in terms of what fan's going to be best. But obviously, if we can go with the right size ducting, we can go with a shorter run. An inline fan is always going to be better, and ideally mixed flow in terms of the style.
And I can just tell you, anecdotally, I've done a number of 8-inch, 10-inch, even 12-inch inline fans, like those Fantechs that were in the picture there, and you will hear them. Like it's just depending on where they're located in the building, but it's just like a low hum. It's nothing like even what a recirc hood makes for noise when it's over top of your range. It's a low hum that you hear off in the distance. It just turns into white noise. There's also silencers that are relatively inexpensive that you can put in line with the flow of the fan that will muffle some of that wind rushing noise that you hear from the fan actually drawing the air through.
By using the flex duct that you did as well, Ben, that'll help muffle some of that sound too. One of the things you were bringing up, Emily, was the preheat, and we didn't answer that. So normally there's no preheat. That's the cheapest, and can be problematic in times, especially in really cold climates or really hot climates or really humid climates. That can be also a challenge. So a lot of the preheats are electric. On one of our current projects right now, working with our mechanical engineer, Positive Energy, they're helping us design a preheat off of our hydronic distribution system. So we have a ground source connection with our heating units, creating hot and cold water, and then the hot water lines will run to the preheat for the ventilate, or for that makeup air. So we've got high efficiency makeup air essentially.
Yeah, we've done quite a bit of preheat systems in our cold climate applications. Those can be, electric heaters. I'm not a huge fan of electric resistance heat, obviously. It chugs, it eats up a lot of energy. It costs a lot to operate. There's other kind of negatives with it, but if you have a condition or an application where you need to temper that air to a certain temperature requirement for comfort reasons, either because you're bringing it directly into the building and blowing it, and you're concerned about the delta T that the occupants are going to feel, or if you have the risk of a frozen hot water coil or something like that, then that might be a solution to solve that. If you're doing, for example, if you're using a boiler to heat your air in the building. You got to be careful about, letting 0 degree air come right into a cold coil, or sorry, a warm coil that's getting cold really quickly. So, so we have done it pretty effectively, but it's if you can bring it in and filter it and and not have to temper it, that's obviously the better approach, and it's less of an energy penalty. One key thing to Ben's point about energy penalty: the kitchen exhaust fan does not operate all that much, right? If you think about the time of the day or the time of the year, how much it actually runs, how much time are you actually cooking? These are typical houses. You're cooking dinner. It's maybe an hour, maybe a couple hours a day. So the energy penalty is not that great when you take a step back from it.
There's been a few questions, including from Michael Ingwe, who's a passive house architect. What do we do when we're designing a passive house? Is there a way to have it? Is there any way to do exhaust ventilation in a passive house?
Yeah, you just give up. It's not possible.
Yeah, don't cook.
No, I think that. Yeah. Go ahead, Russ.
Well, I was going to say, you could do something similar to what Ben already showed. There's no rocket science here, right? If you can bring in the air close to the cooking surface, right, and you can bring it in at a low enough velocity so it's not going to create any spillage or entrainment issues, and we can bring it in at enough airflow, CFM, to not create a negative pressure within the building, that can be done. And that can be done with a low leakage damper, a gasketed motorized damper. It might be a little bit more expensive than the one that was shown in the picture, but this isn't rocket science here, and it can effectively be done. We've done it before. And then you still have your ERV, your general ventilation exhaust pull points from the kitchen as well, right? So I typically separate kitchen ventilation and kitchen range exhaust, right? Those are two separate kind of items that we need to make sure that we're separating.
So Ross, when you have those separated, are you still having the range hood turn on when the oven turns on? Is that controlled that way? Or is that mostly for the occupant to do?
Yes, you could do it that way, right? Just like we're doing a CT clamp on the kitchen exhaust fan. So when the CT clamp, that's a current transducer, right? It's a little donut that goes on the power wiring that goes, basically wraps around the power wiring. When it senses amperage, it closes a relay. So all we're saying is when someone turns on the kitchen exhaust fan, there's basically fan is powered, amperage is flowing, close a contact and bring on something else. In this case, open up a damper, right? You could do the exact same thing with that motorized damper on the oven power, right? If it's an electric oven, you have a CT clamp that has a trigger amperage, same thing. So either one of these contacts, these CT clamps, could engage that motorized damper. So you could have it all run automatically behind the scenes if you chose to, right? It's a choice.
And with the cooktop, like we talked about, going induction lowers the amount of airflow that you're going to need because you're not off-gassing as much. Your food is still going to off-gas some, so you need the flow rate for that. But by going induction over just pure electric resistance, you reduce the off-gassing slightly. By going with those over gas, you reduce it significantly. But by going induction, you're reducing. Also, by going smaller on your cooktop, instead of a 48-inch unit or 36, maybe you can get away with a 30. The other thing that I don't think we mentioned here on all of these designs, usually the capture efficiency is much higher when you're cooking off the back burners because it's further back and it's coming up the back wall there. So that doesn't apply when you're talking about an island, unless it's a back downdraft, which we already said we don't recommend. But if you're, have a hood over top of that on the island, really in the center of your cooktop is going to be your most ideal location.
No offense, Kyle, I have to push back a little bit that we can change our flow rates based on what the fuel source is for a cooktop. What we're dealing with here is airflow. Airflow doesn't care what our fuel source is here. What we're trying to do is create a proper airflow in order to draw whatever it is coming off of that range or oven up into that capture hood. Whether it's gas or electric doesn't matter. Airflow is airflow based on the physical parameters and sizes and, faces of the surfaces, related to that flow rate. So I know everybody wants to think that, induction is safer. And yeah, it is. Induction is safer if you're not running your range hood. But we can't just get in the habit of saying, oh, well, we put an induction range in and we've got an electronic, an electric oven in the house, we can cut our hood size in half.
But isn't the spillage potentially increasing with more combustion?
No, it's all about the physical. And I'm sure Ross, you're the engineer here, you could chime in on this. But as far as my understanding is it has nothing to do with what the fuel source is. We're talking about the physical interface of airflow trying to make its way to that hood.
Well, there's two things here that we have to be keeping in mind. First, manufacturer requirements are going to tell them what their minimum exhaust rates are, right? And most induction manufacturers have less airflow required based on their manufacturer's requirements than a gas range, right? So if I compare a 36-inch induction to a 36-inch gas, manufacturer for manufacturer, most manufacturers of induction will require less airflow. Whether that's right or wrong, whether we want to go to the lower airflow, that's debatable. Scientific community, as you mentioned, Ben, is still kind of, trying to grasp, what's the right exhaust rate. So you see somewhere between 100 and 300 CFM per foot right out of the commercial code, right? So if you're doing light duty cooking or versus heavy duty cooking, you're going to have different CFM per foot requirements by, in the International Mechanical Code and by ASHRAE. So that being said, we do have more contaminants when we have gas than with electric, because we're introducing carbon monoxide, carbon dioxide, as well as nitrous oxides at a higher rate with gas combustion than we are with electric. But that being said, we don't know exactly what the right exhaust rate should be for induction versus gas, right? We're going off of just some scientific data, and we're going off of what manufacturers tell us. So my rule of thumb is basically we need a hood that captures basically as deep as it can possibly be. That can be the full surface area of the cooking surface minimum, and the rate should be somewhere in that 100 to 300 CFM per foot range, right? And hopefully what we can do is we can put a variable speed fan in that might be slightly oversized that can get us to the 250 CFM a foot or 300 CFM a foot, but we can throttle it back. Right. And that we can even do low speed, high speed, or 3-speed, in that way we can have a better understanding and better control over the environment off the cooking surface.
I do know that when we cook and sometimes burn something instead of cook it, the spillage increases quite significantly. So I'm curious, I think in general, your theory stands true, Ben. I think you're probably right, but I think there might be those extreme circumstances where you're charring something or accidentally burning something where you're producing lots of off-gassing, where you might want to be able to increase that flow rate. And then it might not matter as much what your fuel source is anyways, but
and I think
good points, Ben.
I think part of that is also when you're burning something, you become acutely aware to spillage because it's burning, whereas before when something wasn't burning, that spillage is happening the entire time, you just don't know it.
Sure.
So one of the questions that was coming up a lot really early and maybe even during the presentation, and it was asked in a few different ways, but if you can calculate, let's say, like Ross mentioned that the different types of hoods, whether it was, wall mounted or over the island or downdraft or whatever, have different efficiencies of actually exhausting air. And Ben talked about that efficiency, I think, based on like height of above the cooktop of the fan. And so people were asking if there are calculations you can do to accommodate those less efficient situations.
Yes and no. Go ahead, Ben or Ross.
Ben, you want to take that one?
Yeah. So here's the tough part with all of this stuff is, like I said before, the research on this is still so infantile. We know so little. Really some of the good research is just starting to happen in the past year or two. Home Chem, and then Brett Singer's work at Lawrence Berkeley National Laboratory. We don't know yet. And so much of it is also so site dependent because we're trying to put together a set of circumstances to influence airflow. And this might depend on the shape of your countertop overhang, the textures of the flooring that's influencing the friction of the airflow across it. There's so much that goes into this. Sure, I'm sure there's calculations from an engineering standpoint that you can use to try and figure this stuff out. But that's just throwing darts at a dartboard as far as I'm concerned.
There is testing for many range hoods out there in terms of capture efficiency rates, and some look the same and some perform way better than others. There was a chart that we removed from our presentation because of time, but there's many that look all the same. If you compare all the data points, the energy usage, the flow rates, they look very similar, yet perform differently from a capture efficiency standpoint. However, what we do know is that capture efficiency goes up when you do what Ross was describing as oversizing it slightly on the cooktop or a lot, and deepening the volume that it can be captured in. So some of the more modern looking ones, we were sharing a couple texts earlier on some funny looking range hoods that we knew would not work very well at all. But like having a straight up cylinder that's maybe 10 inches in diameter hanging over your cooktop, that's not going to do very well at capturing the plume of chemicals created from your cooking surface. Some modern ones that were like sort of coming off the wall at a slight angle that aren't really pulling and catching and capturing that, it's not going to work so well. And then the downdraft we know does not work so well. The pop-up downdraft cooking on the back sometimes can work, but it's dependent upon all those things that Ben was talking about, and especially dependent upon where you might bring in the makeup air. Like Ross was saying, if we're supplying at the backside right over the cooking surface, it might push too much air out, which would create spillage. So one of the video clip that we showed of Ross's system, that was not a passive house in terms of tightness, but maybe the two locations that I'm intrigued by the most is sort of providing that curtain of air around the outside of the hood that catches most of it for short cycling, and then maybe supplying the rest of it underneath the range to provide the rest of that makeup air. That's what I'm most intrigued by, and I've obviously not seen the data for that. I would love for Ross to do another smoke bomb in that video off to the side to see where the room air is actually going. It's a great demonstration that he did, but it sparked a lot of questions in my mind.
Yeah, and that design came out of right from how the commercial systems are done. Right, commercial systems typically will bring. If you look at a lot of restaurants, you're going to see a perforated surface at the front face of the cooking the kitchen range. And what they're doing there is they're bringing in air at a very low velocity. They're bringing it in to let it drop over the surface of the kitchen hood, and then basically get that capture and then entrainment to bring the air back in and capture the contaminants off the cooking surface. So that's what inspired kind of that design. And I think that's where things are probably going to be going, is, maybe a hood within a hood concept where we can start to get into more like sealed combustion. If you look at boilers, for example, they went from atmospherically vented to, basically power vented to sealed combustion, right? Dedicated air in, dedicated air out. I think if we can start to see, I'm starting to see a trend where we can get to a pipe within a pipe concept, a hood within a hood concept, so that the makeup air is being brought right back to where it needs to be, but we're also doing it in a way that's going to capture all of those contaminants off the cooking surface and be quiet and do all the other things that we're talking about. So, I'm excited about where it's going.
Okay, wait, pause. Sorry, I've been trying to interrupt. It's 7:00 now, and tonight we have a special night with NESEA Night After Hours. So we're actually going to start promoting some people to come on and specifically ask their questions. So for all the people in the audience who aren't usually on, if you start talking over each other, you won't hear anyone. So, just take your turns. And also, there is a raise hands in your thing on the side. If you'd prefer not to be on the screen, just raise your hand and we won't promote you. Otherwise, keep the discussion going. Sorry to interrupt.
So I'll ask another question from the chat. Steve Dimitrik had asked if there is any benefit in treating kitchen exhaust like we treat bathroom exhaust, in the way that, that we use timers, and so that the exhaust runs for a period of time after the activity is done in that space. And so is there any research that shows that kitchen exhaust should continue to run after we're done cooking? And would there be benefit to using that type of approach?
My cheap range hood I got on Amazon, which I wish I did a little more research, does that. It's got a you turn it off and it sort of runs for another 15 seconds. Sometimes when I open up the trash can when it needs to be changed, it's off gassing from there. I push that button real quick and turn it off so that it runs for like 15 seconds or so. But Ross was talking earlier when we were chatting about some ERVs and how they're using those in Europe about capture efficiency and grease catchment and things like that. I think that also apply to this.
Mm-hmm. Yeah, I think that's a interesting technology that may come, hopefully sooner rather than later. But basically, scrubbing technology with ERVs to basically be able to, get, just like we do balance ventilation with bath exhaust with an ERV, or just for the house, ventilation, we could do the same kind of, equivalent with the kitchen range exhaust. So those are both exciting technologies that we're watching.
And I know HomeChem, I saw some mention that they're finding that we should be running our range hoods for about 15 minutes post cooking session in order to continue to clear the, the stale air that's in the cooking space. Something that I'm really looking forward to, and I know it's starting to come out from some manufacturers, I hope it continues to grow, is sensor controlled range hoods. So there's been a number of things proposed, either them using particle counters or IR detectors, so they actually pick up when there's a heat signature from the range or the oven being on, or a VOC monitor or a CO2 or CO monitor, something like that, actually activating the ventilation. So it takes it out of the client's hands. They don't have to worry about it anymore. We don't have to worry whether or not they're actually using it, and we're assured that these ventilation rates are actually happening while they're needed.
I'll just add that commercially, that's how they do it. And a lot of systems commercially already have that technology, which is great, right? If it senses heat, for example, and it knows that someone's cooking, it activates the exhaust fan automatically. And then there's also a study that I should mention, the ROCIS study. Google search that one, ROCIS. I forget exactly what the acronym stands for, but that was a great study that looked at leaving the kitchen exhaust fan on for 15 or 20 minutes after the cooking was done. To get all that air change and get that exhaust contaminants out of the kitchen was vitally important. So it's been studied quite a bit. I'm staring at a lot of faces here.
Yeah, well, just quickly, apparently the Zoom only allows us to have 100 panelists. So maybe if anybody who doesn't want to be on screen will de-promote you so we can get those who do want to be on screen on. So sorry for the confusion. This is new for us.
So hi, this is Jody. In the conversation, somebody asked or mentioned how people don't, at the very start of your presentation, you mentioned how people don't use their exhaust fans, and part of the discussion was about making it automatic. But the other part of it is behavior change and education. Whose responsibility is that? How can we make sure that people are using their ranges and the exhaust fans the way they need to for good health?
I would say part of the responsibility is ours as the consultants, builders, architects, mechanical engineers. We need to be pushing for that, and hopefully eventually it slightly becomes more automatic. But I think the question becomes, what is automatic? Is it just connected to the cooktop? Is it connected to the oven? Is it connected to a bunch of different devices? I think as much as I would love to educate everybody on this and everybody to understand all the ins and outs of this, it's probably not going to happen. So we need to have some automation, I believe, to take care of some of these issues.
Yeah, I think codes are going to help. Codes aren't always the answer, but I think codes are going to help in some of that. And also third-party, testing will help. HVI, the Home Ventilating Institute, is hoping to get basically institute testing for capture efficiency off kitchen exhaust hoods. And they're also going to track zone level, sound level, et cetera. So if they can start to put together some real data that looks at capture efficiency, sound, airflow at different static pressure requirements in different duct systems. So you won't have the issue that Ben talked about with an 1,000 CFM exhaust fan that's only running at 200. Those are the kind of things that I think will help a little bit.
And I think for right now, it really does, fall on us, like Kyle said, to be educating the client. Hopefully in the time that we as builders spend with the client working on their project, we can impart some of this. And then another practice that we do here is we actually give a homeowner's manual to the client at the completion of their project, going over all the systems. And there's a section in there about how important it is to make sure that they're running their range hoods, how to maintain their grease pre-filters and that type of stuff, and just try and set the client up for success as much as we possibly can.
I actually agree with Kyle in the sense that I just posted a little while ago that in the last 2 years, I have not designed a house that didn't have induction cooktop or at least electric cooktop. And I believe it's a commitment from the architectural and design community of educating the buyer of what is good and what is not. And if you're successful at educating and provide data and provide information to your clients, it shouldn't be that hard. If it's not that hard to convince them to do energy efficiency, it shouldn't be that hard to convince them to do a healthy house too.
Mm-hmm. There's only a handful of senators. The place where I have issues with that, Armando, is when we're in like just a renovation, like a kitchen renovation situation, where we may not be in there with the expressed intention of, you know, changing the envelope of the building. We usually do, but sometimes you have a client that we're just in there to do the kitchen. They want that gas range that they, you know, you can't break them from it. In those situations, it's harder to do that. You know, when we have clients that are doing whole homes with us, then we always try and push them towards induction. And by no means with my comments to Kyle before denigrating induction cooktops. I'd much rather see induction cooktops in a building, no matter what.
Yeah, I don't do remodels, so I don't work on remodels, so that's not a problem for me.
Smart man.
I think part of the point you were making, Ben, was that it's important that we're designing for all of this regardless of the cooking type. It's still important to do all of this correctly. So I think you're spot on in terms of that sense.
I think there's a real issue about how all of this stuff is marketed. I mean, when you go to buy a stove, you buy a stove, and then the salesman says, oh, you'd want to have a pretty exhaust hood. And nobody hires engineers to actually get it right. And, you know, if you buy a toilet, it's got an outlet where the poop goes down, and it's got an inlet where the water comes in. You're selling part of a system. And what I don't understand is why with the stoves, you can buy the stove that's got the input of the gas or the electricity, but nobody worries about the output, which is all of this gas and everything else. And that surely they should be paired. They should be one unit. You can't buy a stove without buying a hood that is properly paired to it, and take it out of the hands of the appliance salesman and put it in the hands of the engineers, and just stop this stupid system where they're treated as separate items. They're not.
Lloyd, you know, I completely agree with you. And I think that's where that third-party testing is going to help, right? Just like the miles per gallon sticker on the car that you buy, right? Or the HERS rating of the house that you're building or buying. Those types of you know, energy labels help get the conversation going in terms of what's the right fit, right? If I could pick from a menu of different hoods and know their capture efficiency, knew their sound level, knew their exhaust airflow rates, if I knew all that data, I could make an actual educated decision on which one I want to go with, right? Right now, you know, it's comparing apples and oranges, and it's all based on the look and the price, right? There's no other data that's provided on these spec sheets other than a nice glossy photo, right? And that's part of the problem.
I personally, I hope that somehow I can intervene in the course of the project design phase where I can kind of help to influence those selections, because other times if I'm leaving it up to the designer or the client going to the appliance, you know, distributor, seller, I don't know what's going to happen, what's going to show up, and I have to try and figure out how to make that work, and that's tough. So hopefully we do get some sort of standardization across the board on this, because it's really frustrating to try and pay a lot of attention to the IAQ of a building and the envelope of a building, and then we have a $250 Amazon range hood show up, and that's what they want.
Right, and the problem is that a lot of people don't even know they have a problem.
Everything. Mm-hmm. That same theory applies to all facets of this building industry that we're involved in, and this is just one of those challenges, and it's a big one because of the health risks.
Yeah, I think it's good to keep the context alive that everything in the building is a system, and everything affects everything in the building. So, you know, I was joking around with our team. It's like you're only as good as the weakest link. So if we get the kitchen exhaust wrong, or if we get the makeup air wrong, if we get any of these systems wrong, they're going to have other domino effects that come into play. And so, so just, we got to do it right. We got to start to a systems approach.
And make sure it's executed correctly as well. Design is really important, but installation is also extremely important. And then long-term maintenance of the system, which is usually an afterthought.
Commissioning,
Yeah.
like I said before, I'm the weirdo that throws a flow hood on the discharge of the range hood to see what it's actually doing.
Mm-hmm.
That's not normal?
Everybody that I've talked to looks at me cross-eyed when I say I do that. We need to be doing that.
Agreed.
Has anybody tried the Panasonic Cosmos system, where it does have the sensors and it can relate to the bath fans and also the exhaust and the makeup air? I've heard about it, but I haven't actually tried it out myself yet.
Same here.
Yeah, I've read about it. Have not seen or played with one yet.
I generally just, this isn't, a sales pitch for them, but I generally trust Panasonic and their ventilation department. They seem to be really on the ball with everything that I've ever dealt with in any conversations I've had with anybody from them. So yeah, I'd like to get my hands on one of those.
Yeah, my main concern is about the sensors. What sensors are they using? What's the calibration of those sensors? How do we know that it's working correctly? What's the minimum turn down that it will allow the fans to go to? How do you know if you have a problem, right? So that's there's pros and cons to automatic systems, and automatic systems are great, but when something doesn't go right, how do you know? So part of that's commissioning, right, and proper evaluation over time, right? So the other part of it is I don't even know what sensors we would want, right? If we measure VOCs, that's part of it. Particulate matter, that's another one. Do we want to measure formaldehyde? Do we want to measure carbon monoxide? Do we want to measure radon? Do we want to measure, so this is more of just air quality, just in general. I'm a huge fan of data and a huge fan of sensors, but when it comes to our health, we need to measure a lot of things, right? And we don't even know the extent of all the things we need to measure to make sure that we're getting everything captured correctly and running ventilation correctly.
Curious, Ross, if you could talk a little bit about what sets your FUBOT off and how much you've played with that, with some of these different elements that are off-gassing.
Similar to Ben, I'm a geek and I've got a lot of sensors and I play around with a lot of things, but yeah, FUBOT's been a fun one. Just, turning on the oven, turning off the oven, running the gas range that I have in my house and running it with or without ventilation, with or without makeup air, and just try to play around with it and see. And it's the particulate matter, the PM 2.5, it just skyrockets. You turn the oven on, you turn the gas range on, even with or without ventilation, it goes up, and it goes up pretty dramatically. And so the proof is in the data. It's cooking is hazardous. We know that. Yeah, I don't know how much you want me to, how much more you want me to share, but yeah, there's a lot of stuff there.
I have a question, a comment about commissioning and testing or verifying these. It's when we do field testing, it's very difficult to get a capture hood to fit these, and each house you walk into has a different size hood with a different layout. So they almost have to be custom made for each individual kitchen and system, and that becomes problematic for us, the testers. My question to the panel would be, if you have a kitchen with hooked up to an ERV with kitchen ventilation at like 30 CFM or something like that, how far away do you need to position that register away from your range exhaust system?
I like to get at least like 8 horizontal feet if possible across the floor. And a lot of that does factor into based on what the range ventilation actually is. If we have a very possibly poorly performing undersized range hood, then I'm going to try and push it further away. If we have a really well designed range hood, I'm going to try and I'll be comfortable with it being a little bit closer.
Okay, a follow up to that would be multifamily housing or open floor plans. That becomes a big problem in terms of positioning these things, and how do you size your exhaust hoods for a multifamily facility?
So, I'll answer that. For multifamily that we work on, we size it no differently than a single family house. We got to know what the cooking, what the cooktop is, whether it's induction, whether it's gas. We start with the manufacturer's requirements, and then we always apply kind of our safety factor for a variable speed fan on top of that. Budget's going to dictate a lot of times what we can do. I would love to do remote inline blowers in every project. It doesn't always become the case. So hopefully we're trying to get to ECM, variable speed that are quieter, lower in the zone levels. And to your earlier question about commissioning, you might not be able to get a velometer or a hood on the actual intake side of the kitchen exhaust, but you can definitely get one on the exhaust termination on the outside of the building. And so that's where I would recommend we measure the airflow, at least on the exhaust side for the kitchen exhaust, as well as on the intake side. I've done it that way with the typical velometers, the typical hoods. And Ben, I'm sure you've done it that way as well.
That's generally my approach. And the one thing I'll say is just bring some extra thick, like weather stripping gasket with you, because if you have something like clapboard siding or something like that, you may want to throw some extra thick gasketing on the the ring of the capture hood just to get a better seal around it. But yeah, I'm generally testing at the wall cap. And granted, that can be tricky if you have, a second floor discharge or something like that and you don't have a ladder with you. In that case, bring a piece of cardboard with you and some masking tape and tape off the hood and just cut out a hole in the center of the hood that's about the size of your capture hood. Is it perfect? No, but will it at least be a measurement that you can reference against? Yes.
Yeah, and you can compare with traverse readings across the surface of the hood as well. Mm-hmm. So you can at least get two forms of input in terms of data.
So Ross, you're putting the same size exhaust hood in a 700 square foot single bedroom apartment that you are in a detached 3,000 square foot house, and does that not provide problems?
No, so it's all based on the cooktop. Right. So is it a 30-inch range? Is it a 60-inch range? Is it gas or is it induction? So the cooktop to us will dictate what size hood we have and what exhaust rate we have. So I'm less concerned about the size of the building. As long as we've got that with makeup air, problem solved.
Without makeup air, it becomes a huge challenge, David. And it's, the makeup air makes it balanced is what the key is there. And it should, if designed correctly and installed correctly, have little impact no matter what your size is. It's when it's not done correctly where it does make a big difference depending on how that impacts the space. And so the larger the space, the less the impact.
Yeah, makeup air can be really challenging in multifamily buildings. So I will just throw that out there. It is challenging.
And just a thought, when you're dealing with a small kitchen in a multifamily like that and you have an ERV exhaust somewhere in the kitchen, something that you can do if you can't get it far away on the ceiling from where the range is, if you drop it onto a sidewall and bring it a foot or two down off of the ceiling, then you're less likely to be capturing that hot contaminant laden air off of the ceiling and contaminating the core. Is it the best situation? No. For getting the pollutants out, is it going to protect the ventilation system and make sure that the ventilation system keeps running? Yeah, so it's kind of the lesser of two evils approach.
Yeah, we've done that with some passive house projects, and we've added pre-filters on the ERV system so that we're going to try to grab any grease or anything a little bit more hazardous on a pre-filter before it actually hits the ERV core.
Hey Rose, I have a question for you. Is there any video studies of different fans? Usually I see is that they're cooking or they put a pot on the back of the stove. Obviously that's where there's more collection. But are there any videos with all four burners cooking and seeing really what's effective on the front of the range and on the back of the range?
So
I'd like to see that.
There's a ton of video footage and studies done on commercial gas cooktops. That has been studied quite often and quite a bit. And they look at it from different angles, and you can see exactly where those contaminants are coming off the cooking surface. And that's how they measure in commercial systems spillage. how much of that contaminant off the cooking surface is actually making its way into the hood and how much of it is actually spilling out of it. That's how they start to measure that with that and tracer gas. So there is some of that. Some of it is behind a paywall. So to get access to the research data, some of it you have to pay for, but that's been definitely studied quite a bit in commercial, less studied in residential. And I think that's where we're starting to see, with Brett Singer and some of the Lawrence Berkeley Labs stuff, that's where it's going. So we're going to get more data over time and better imaging.
I've seen videos on home chem as well as Corbett Lunsford doing videos talking about home chem on YouTube. So you can certainly watch some of it there.
I forgot the home chem, you're right.
Yeah, none of it's really phenomenal coverage like you're asking about, but there is definitely some info there. And it's all still, the research is in process as we speak right now. So hopefully,
my understanding, home chem is one of the first grants doing that type of work at that level of detail. For residential studies.
My cheap and way to do it is get one of those little smoke grenades that we showed in the video. Put it on a pot on the cooking surface. Put it on the front burner. Put it on the back burner. Put it on the side burners. Try it without makeup air. Try it with makeup air. Try it with the window open. You can start to see how the airflow patterns get affected, and those smoke grenades are they're a couple dollars. So it's not a scientific test by any means, but it's a way to get an understanding of what your real life situation is.
Ross, back to sort of the hood size and shape. In your original presentation, you said the deeper the volume of the hood, the better it captures. And just I was curious about the specific hood shape. I mean, obviously, width is good. I always try to convince clients that the stylish thing now is to make your hood 6 inches or 12 inches wider, making it deeper, front to back is more of a challenge. But then there's the super clean modern hoods are basically flat on the bottom. Commercial style hoods have a recess. Does that recess matter? Have you noticed, or I guess it's a question for anybody.
Well, yeah, I can tell you that the larger the surface area of the hood and the deeper the volume of the hood, the better the capture efficiency, right? So the capture efficiency is what's going to measure how much you're going to capture. And that is going to be hopefully coming out soon with HVI testing on market available, ready, off the shelf hoods. If you go, with less square footage and you go with one of those modern sleek ones, you just don't have the capture efficiency. You're going to have a lot more spillage where it's just not going to, get into the hood. You're not going to get the contaminants out. And you'll see that from some of the studies that we mentioned earlier. The ROCIS study. Kyle, do you remember what the acronym is for ROCIS, or Ben, or anybody on the?
Don't offhand.
Yeah,
look it up.
I can look it up as well. But it's a great study.
How do the grease filters affect that, Ross? Because a lot of the grease filters are right at the bottom, basically stopping that volume, if you will. It ends up being a flat surface. Does that impact that volume calculation a lot?
It absolutely does, especially if those grease baffles are not cleaned, right? The best ones are the ones that they do commercially, or the residential ones that do it like a commercial system, which is at an angle. So when you angle, so if you can envision those grease baffles horizontally versus angled, the angled ones obviously increases your surface area and gives you more volume. So you're going to capture the contaminants and give it time for it to then make its way through the baffling system. So you want one that's not flat. You want one that's actually angled. And so that's why the deeper the internal volume of the hood, the better the capture rate.
It makes me think a conversation Ross and I were having before this all started was about maybe we need to think about this, the future of range hood design more like a fume hood for a chemistry lab. And thinking about chemistry labs, they're almost always at an angle from what I remember inside. So increasing.
There's a reason for it.
Yep.
Yeah. So we just need that fun pull down door in front of our range for cooking.
Right.
I'm for
you need
it.
to step inside the room of the oven, or go outside to cook.
Put on your oxygen mask when you cook.
Yeah.
There's a lot of funny pictures I almost put in the presentation with that.
I know there's more questions.
Somebody's got to have something.
I've got a whole list here. I was just
I was gonna say,
didn't want to dominate.
John, you had a question.
Sure.
Yes.
This is so fascinating. I feel so bad that I missed the first hour. I had another meeting, but
Oh, John.
I'm happy to watch the video if this already got covered. So feel free to skip over me. But I'm curious about makeup air filtration, like the filtration, pressurization with fan, heating system units. You know, there are different manufacturers out there who are putting together kits where you put the components together. There are ones that are sort of like a self-contained unit. And I'm curious about how that, like, the heat, the pressurization, and the filtration plays with everything we're talking about and bringing new air into the space, and kind of how the best way to route those types of systems are and how good they are. I'm just very curious to know how to employ or whether to employ those.
Yeah, so we touched on some of that. I'll jump in, I guess. We use them on a lot of our projects where we think it's required in cold climates where we need to preheat the air for comfort reasons, right? Or if we're worried about a frozen coil in terms of a hot water coil system. So what's important to me is that we have a motorized damper that's going to shut off the outside airstream, right, when it's not in operation. That's going to be a gasketed, low leakage, ideally class 1 if you can get it, but just a low leakage gasketed damper is very important there. A pre-filter, right, that's going to capture any insects or any type of debris that might make its way in to it. It's all going to be insulated ducting, and it's got to be smooth internal walled, hopefully not much on the flex ducting side. And then you got your fan. And then you have your electric heater or not, depending on the application and where you're bringing that air in. What we talked about earlier, and Ben had some good photos about that, is if we bring the makeup air in the right location, based on the right application, we don't need to heat it. But if you're bringing it in an area where you're going to be blowing 0 degree or 30 degree air directly on people's feet or directly on people's heads, or bringing it in especially at a high velocity, you're going to get comfort complaints. So the devil's in the details and really the execution of where that air gets brought in. If you can bring it in underneath the gas range, or you can bring it in multiple areas, those are going to be, I think, lead to more successful installations. And I'll shut up.
Yeah, so John, just to kind of touch on something that you missed. So my two preferred locations are, the one I'm currently on to is bringing it up directly behind or underneath the range, or in either of the toe kicks adjacent to either side of the range. So, and the common complaint, we touched on this before, is that everybody says, oh, you're going to have cold toes and drafts. I've done this, I can't tell you how many times I've yet to have a client come back and say, oh, my toes are cold.
Right. I think the key thing that Ben's design that he's talking about is he doesn't have a fan that's bringing in the air. Correct me if I'm wrong, Ben, but I believe it's just a motorized damper.
Yes,
so when the motorized damper opens, it's going to let air come in, but that's great because it's not coming in at a fast velocity. Mm-hmm. I think you would get the complaint if you put a fan on that instead of blowing 0 degree or 20 degree air, at a very fast velocity at someone's feet while they're cooking. So if you can bring it in low and slow, that's going to bode well for the thermal comfort.
In your opinion, Ross, when do we need that fan?
It depends on the design. If you have if you've got an application where we can't bring basically the outside air directly to underneath the gas range or nearby, or you have a really, really long duct run, or if we are, because of, architectural structural constraints, we can't get it to where we want to get it. In those cases, we might need to have a fan installed that can run, and we might need to preheat it. So it's going to be application by application. I wish there was a kind of just an easy solution for all projects, but it's just not the case.
Sure.
There was a question or a comment earlier about automatic hoods that will turn on whenever the stove is turned on, not just when they sense the fan turned on. And then a related question would be with ovens, the idea of using makeup of having the vent turn on when the ovens are running. Kramer actually mentioned that ovens don't run continuously; they modulate on and off. I'm wondering if there's for both of those things. I wonder are there any of these switches that are on timers, or should there be timers that would the modulating ovens would help spread the time out, and just with generally clearing the space? Are there fans that are on timers made for kitchens?
There are fans on timers that are not operating off of sensors. I'm sure you could arrange, a relay in a box or set to a timer with a current transducing clamp like we were talking about before to make this happen. I think to go back a little bit, talking about hood and ventilation systems that are using sensors, I think the sensor that I have the most faith in is just an IR sensor. Like, as this technology moves forward, because what we're talking about here is any of these byproducts that we're going to have are going to be the result of some sort of heat being applied to them, or the heat of combustion. So if we have something that's just simply watching the temperature of the range in the oven, then I think that's going to be our most foolproof way to activate these things. They're also probably the most reliable sensors over the long term, versus something like a VOC or a CO sensor that's going to degrade over a period of years and then have to be swapped out, hopefully. So I don't know anything off the shelf yet that would do that. It would be like activated by the current sensing of the range or the oven coming on, and then running for 10 or 15 minutes, figuring that's going to overlap the cycle time of the elements or something like that. That's also my concern with, you can't really do a CT clamp on a gas range, because the only time that it's really drawing power, unless they have the oven light on, is at that time when they turn the igniter on at the first 3 seconds of lighting that burner. So the only current that you're really seeing through that thing is only for that brief couple of seconds.
Yeah, I think where the questions about where the future's going, there's these electrical monitors that can see and detect signals, spark ignition on an electrode, for example. When you light your stove, the click, 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 the ch-ch-ch, sound that you hear with the gas range. And so, so Ben, I think where it might go is, if it sees that type of signature, it may be smart enough with the little AI to say, hey, you know what, someone just turned the stove on. Maybe I should turn on the kitchen, exhaust fan.
The way a Sense monitor or something works.
Sense or Emporia View or one of those. Yep, exactly, where they're getting this AI and the smarts built into it. But I've got a couple in my house, so I play around with them, and there's pretty amazing stuff, which what they can tell you what's operating inside of your house. It's nice to see the heartbeat of your house in terms of how much electricity it's using real time. But we'll end that.
My Sense can't get 70% of my usage because of electric vehicle charging, as well as mini split heat pumps. It just sort of doesn't calculate those right.
They're terrible with heat pumps.
It's variable speed compressors. Any variable speed load they're really bad at, because the variable speed signatures are really hard to detect because they're always changing, right? That's the advantage of an inverter heat pump. It's an advantage of an electric car charger, is that it modulates, right? And so Sense or any of those devices really have a hard time to say, oh, that's the car, or oh, that's the the heat pump, because they throttle up and down. But back to the original question. Yeah, some LED lighting gives it trouble too. So, but back to the original question is, we use an Eaton split core CT clamp off the shelf. I think it's like $30, $40, something like that. We can put it on the oven. We can put it on the kitchen exhaust system, and when either one of those sees power, it kicks on the makeup air or just opens a damper. So it's a really
do that at the panel, Ross?
You could do it at the panel. You could. You could put it anywhere on the power line. So whether you want it at the panel or whether you want to put it closer to the actual fan or at the oven, but either way, if it's on a dedicated circuit, you can do it right at the panel.
Yeah, I use what are called RIBs, relay in a box. It's a standard industrial product that you get from Grainger. Yeah, ribs.
Functional
technologies
devices.
Functional devices. And basically, all it is it's a little box with a relay set up in it. I get them to feed 24 or 12 volt to whatever my transformer is for my for my damper. You just literally put it around the wire, or you can hook the wire to it for the source. And it will just kick on whenever it sees voltage across it or current across it.
If you really want to take it a step further, you can add a delay break timer so that when it senses that the current has ended, meaning someone theoretically has stopped, cooking, you can leave the fan on for an additional 15 minutes, 20 minutes or something like that. They do it very commonly with bath fans, right? You hit the switch, it stays on for another 20 minutes or something like that to get you that extra ventilation. So
There you go.
that's a slick way to do it. Granger sells some Omega delay break timers. They're like $6. They're really cost effective,
Bill Robinson, I'm sorry, has a good question. I know we're all cold climate New England folks, but Bill's down in New Orleans where, it's a little bit hot and humid. Any concerns or thoughts or approaches for bringing in all that hot, humid air?
Not worried about preheat, that's for sure.
Dehumidification.
Dehumidification.
Yeah. As many people have mentioned on the BS Post Bear, podcast, or it's all about dehumidification, keeping the building dry. So if you're bringing in 95 degree, 80% relative humidity air, for prolonged periods of time, your cooling systems are going to have trouble keeping up, and you're going to be just flooding your house with water vapor. And so, you got to get a dehumidifier on the makeup air system.
And you want that makeup air to short cycle as much as you can, so that it's being pulled out.
Yeah, so Bill, deliver it as close to the exhaust as you can, so it's influencing as little of the rest of the building as possible,
while still
getting
high capture efficiency.
Yeah. Bill, we're all in New England, or Kyle's between Rhode Island and Pennsylvania, and Ross, I assume, is in Massachusetts or Rhode Island.
Mass, yep.
Mass, yeah. So we're New Englanders. Ben's in Maine.
It's a good question.
Have you guys used the one time I got sort of deeply involved or semi-deeply involved in the makeup air switch? It was a Venturi switch that just sensed when there's air moving through the duct. Is that a current technology? Is that an older approach? Is it simpler, reliable? Are there pros and cons?
Yeah, are you talking about like a pressure sensor mounted in the exhaust duct? Yeah. That's, some manufacturers still recommend that. I'm not really sure why. You're putting a probe with an electromechanical device in the grease, airstream, and relying on air pressure to kick the makeup air unit on and off. It's a relatively simple device, but to me, the current transducer, right, the CT switch that we've been talking about, I think a lot on this call, I think that's the more, to me, it's the more robust solution. I don't know if Ben or Kyle have any thoughts on that, but that's the one that we typically gravitate towards.
Okay. I'm pretty agnostic personally. I don't mind the pressure switches like a DeJournlund or something like that, diaphragm pressure switch. They're cheap as dirt compared to like a rib box or something like that. They're definitely cheaper. So if cost is a factor in what you're trying to accomplish, then there's something to be said there. But when we're talking about the difference between $20 and $100 or something like that comparatively. So,
have you seen any durability issues with that, Ben?
And you know what, and it was when I first started using them, it was a concern of mine. The same thing is, it's like we have what's presumably a rubber or silicone membrane and a diaphragm switch that's going to be in a hot, greasy environment. I haven't seen any fail yet that I know about.
Good.
Yeah.
And just earlier, you guys may have just discussed this. I was distracted bringing people on, but any thoughts about locations of the exterior wall cap, or putting it on roofs, or type of wall caps? Are there ones you like, ones you don't like, installation techniques, etc.?
Yeah, I mean, I can answer it unless, Ben, you got suggestions there.
Go for it.
Yeah, so I'm surprised we haven't talked about it yet on this call. But yeah, intake locations and exhaust locations on the outside of the building are super important. code mandates, or most code, the IRC, and that's adopted by most states, recommends or mandates 10 feet between intake and exhaust. The intake is the most important thing. They're going to make sure that's getting clean outdoor, quote unquote, fresh air from outside. So at least in the northern climate, we got to get it above the snow line, right? We don't want it buried down low. We want to keep it away from any source of contaminants of any kind. And we want the closest duct path as we can possibly get. I typically prefer wall vents over roof vents. One just for, it's another water penetration through the roof. Sidewalls are just, more durable. We can do typical, wall vent caps, like you see, like a dryer vent with an insect screen, and that's just a nice way to do it. On the exhaust side, you got to get it away from, operable windows and doors. You got to get it away from intakes. And so that would obviously typically goes out to the wall as well, but sometimes it has to go up to the roof. Obviously wall vent preferred. And typically there's a backdraft damper on those to make sure that they seal. There are better gasketed ones in the backdraft damper category that we recommend. The ones that you can hear, sometimes you can hear them chatter. If you don't have a gasketed version, you'll hear when the wind is whipping, you'll hear it go like, it's the metal on metal of the backdraft flapper. And that's why we recommend the gasketed versions. The other thing I'll just add is that with kitchen range exhausts, they have to be run as a dedicated duct system. They should be smooth interior walled. And they have to be, galvanized steel, stainless steel, or of a certain similar type of metal. And so, I highly frown upon any kind of corrugations, any kind of flex duct, any kind of anything that could capture and hold grease in it. That's very important and be a fire hazard down the road.
For those backdraft dampers, Fantech makes very nice ones. They're the gasketed butterfly style backdraft dampers. I try to avoid going through roofs at all costs and go to sidewalls. Getting the distance between intake and exhaust can be difficult sometimes due to limitations inside of the attic or wherever you're trying to discharge from. So I just try and separate them as far as is feasible. For wall caps, I've recently discovered a company called Luxury Metals. They sound expensive, but they make really nice, really nice sheet metal wall caps.
We use those a lot, Ben.
Yeah, they're really nice, and I just found them on this project, and I'm in love with them. They're not wildly expensive, but they're what you think a sheet metal wall cap should be.
And you can get them in stainless steel and copper if you want to splurge.
Yeah. Yep. I get them in galvanized and just prime and paint them to match the side of the house.
Beautiful.
Any thoughts on planning for maintenance, both either on the design end or installation end? Are there things we should be thinking about to clean the ducts, maintenance schedules, best practices? I've only torn apart old ductwork, and they're always just caked with a half inch of grease. So I have to imagine that's not a good thing.
I'll let you take that one, Ben.
Thanks.
Nobody wants it.
I'm just, first off, the first battle I'm trying to fight is getting good systems installed. That is something that's definitely been ticking in the back of my head. It's also like, how am I going to get a homeowner to check that the backdraft, that the makeup air damper is in fact functioning? It's a tough question. How are we going to get them to maintain that?
I think there should be a servicing agreement with every project.
Yeah,
the builder is involved in that, or the mechanical installer. It happens with fuel burning, boilers. It should happen with heat pumps and all of these different pieces of equipment. They should be maintained.
It happens with your gas generators, backup generators that you install on your buildings. I agree. That's something that I've been kicking around a lot recently is, something that I do currently when we finish a project is I'll create like Google reminders with the filter sizes of like any of the HVAC equipment in the building and set them up to ping the client every 6 months for 2 years, just to say, hey, it's time to check your filters. Here's your filter sizes. Just to, I don't know. I don't know what we do. I don't know how we ensure this. I'm of the school of mind that they keep it simple, stupid. That's why I have gone to the methods that I have. I want a really low tech, simple system so that there isn't anything difficult to maintain or any complex, expensive parts in the process.
Yeah, simplicity is important. And I'll add that if it's done right, you're talking about a kitchen exhaust fan that you know if it's not working, right? You turn the fan on, you can feel it at the hood, whether it's working or pulling or not pulling. So that's an item that can be easily checked. And on the makeup air side, hopefully you have a visual indicator on an electronic damper so you can see is it green or red with, so that the homeowner can just, hopefully check it once a year or twice a year, just make sure that the light turns, from red to green when the kitchen exhaust fan is active, or just put their hand, in Ben's example, put your hand behind the gas range or, cooktop or whatever, and see if you got air coming in when the hood is active. Change your filters like you would change your HVAC filters. No difference there. So, but maintenance is definitely one of the things that's lacking, I think, across our industry, where people it's not front of mind for a lot of people.
This is going to sound really silly, but I've talked about this a couple of times in the podcast recently about putting a QR code in the mechanical room, just on the wall or on the door, that links to not only a house binder for all of these systems, but it automatically puts those things into your calendar. I mean, most people have a smartphone now that sends kind of reminders and alerts and things, because somebody posted in the chat box earlier about how when there's house turnover, so say you're not the first owner, you're the second, third, fifth owner of this house, like sometimes those binders don't go with it, or sometimes you have something where I went and did an audit on a double envelope house, and the people that were living in it at the time had no idea what it was. So still not a great idea. Was kind of a cool thought, but not a great idea. And so how do we make it really simple where it does automatically put that reminder in for you that says like, hey, change your filters or check your filters, or call the HVAC contractor to blow out the, compressor, or check the light on your range vent hood. And here's how you do it. And it's a simple step, or it's a link to a short video, like I don't know about everybody else, but if you don't know how to do it, you Google it on YouTube. YouTube will tell you how to do things.
Something that I've kicked around in this same kind of vein, and I've yet to do it, but kind of like, ResNet and some of the codes are making people do now is posting it on the inside of the electrical panel cover. How we have to have like now by code, and for ResNet, we have to have like the window U values and the wall R values and stuff like that posted inside of there. Just doing, like you're saying, maybe a QR code, or I don't know, a link to a permanently maintained Dropbox file or something like that with like, here's the operational manual for your home, something. I don't know.
Or
two things.
I was going to say, a lot of the insurance apps. So like if you have home insurance on your house, they often have the apps that like you can walk around your house and you can take pictures of all the things that are in your house, that in the event that you had some kind of issue, you have some kind of documentation. I would feel like it should be pretty easy to create some kind of app that would do that. So maybe the QR code just links to an app that downloads all that information for you. I don't know.
So there's an app called Centric, CENTRIQ. We actually showcased it on This Old House maybe a year ago. And with that app, it's a smartphone app that you download, iOS and Android enabled. And what you do is you take a picture of the rating plate of the appliance that you have. And what it will do is it'll pull down all the manuals, all the replacement parts, kind of everything about that appliance. And it basically creates a digital organizational folder for your house. And so I have it for my house, and, I think the information there is invaluable. If we were ever to sell our house, like, the buyer would love to have that information. So there's value there. And so, I think it's a great suggestion. And so I would check out, not a plug or anything, but that's one company that's trying to do that. Centric, CENTRIQ. And the other thought I was going to throw out there is, hopefully with Sense and Emporia View and some of those products coming out with diagnostics, hopefully they'll let you know of a problem before you know it's a problem. Right? If it can detect the electrical signature of your heat pump, and it knows your heat pump's running 20% more this year than last year, or it can see a misfire on a furnace, hopefully it's going to start to, the fan power's 30% more this year than it was last year. Why is that? Maybe it's the filters are plugged, right? So it can start to give you kind of advanced analytics into pinpointing what's the problem with your house. So I think that's hopefully a big part of our future as well.
So this is Miguel here from Positive Energy. I have no idea how I became a part of this. I came on late, but I'm happy to be here. And I wanted to point out, a lot of this discussion is centering around the idea of setting really good expectations with clients very early in the process. And in the same way an architect would program and go through programming exercises, design exercises with the client, I think it's valuable to do that from a mechanical perspective too, to help people understand, like, here are your priorities and goals. Here are the strategies that we're taking to meet them. And here's what you can expect out of this system through time. And here's who you can contact whenever you do have issues. So regardless of kind of what the minutia is in between and how you're getting service calls brought to bear, a lot of that can be kind of woven into those early conversations so that the outcomes, when they happen, result in less callbacks. And actually, people have a very good understanding of what it is their house is doing and who to call when it's time to get it serviced. That's all I had. Also, how am I here? Who did this?
Everybody's a panelist tonight after we presented.
It's so fun.
It is. It's totally about, training your clients and educating your clients about as much of this stuff, because we're building houses that are radically different than even 20 years ago as far as the amount of technology and systems that are packed into them. And there is a big responsibility on us as the builders and the architects and the engineers to make sure that we are trying to educate them throughout that whole process. And it's kind of a mixed bag as far as the uptake of different clients goes. Some of them are totally into it. They want to know all about everything in there. Others, it's, I don't care. It's what's the tile on my bathroom wall. They could care less about the ERV. They know we put one in and it's going to beep at them every now and then to change the filters. But it really is our responsibility to try and do our best to educate them. And like I said before, we put together, the house binder at the end of the project to at least give them a touchstone if they have to go back to, and we leave them with, numbers and contact information for all the subs and everybody that was involved in the project that installed anything in there. And we try and, instill to just call us. If you have a question, call us, so.
Yeah. One thing we've had success with too is getting a lot of feedback from installers in the design process, particularly around service. Most installers I've ever spoken with make the majority of their money on service calls, and so if those service calls can be easier for them, that's even a higher profit margin on that part of their business. So we regularly do feedback roundups with our installing contractors across the country to try and understand what can make your job easier when you actually go out to service these systems, and then we plug that into our design process, and that's feedback we can deliver directly to an architect. So it works really well when you can kind of close that loop, but it's not commonly done. This is a relatively new kind of area of connection, I'd say, in the industry, from architecture to the installing boots on the ground.
Okay. Hey, Miguel, if you wouldn't mind answering a question for us. We were talking about Makeup Air in New Orleans earlier, and all of us are in the northern part of the country, but you guys are down in Texas. And from a high humidity standpoint and Makeup Air, are there specific challenges or concerns that we need to be worried about? Up north, we're worried about preheating that air. Right. Down south, we're worried about dehumidification of the space. But I was wondering if you could just mention just real quick on that.
I mean, the strategies are virtually the same. We don't need to preheat, obviously. But if you don't have dedicated dehumidification, your shoulder seasons are going to be miserable every time you cook when you turn that range hood on and the Makeup Air system kicks in. So it's sort of the same logic as having an ERV. If you don't have a dehumidifier first in a hot, humid, or mixed humid climate, the chances of your indoor conditions being very uncomfortable and potentially causing moisture issues are high. So have a dehumidifier first, and your Makeup Air system, any other supplemental ventilation strategy like an ERV is going to work quite well. And there are some kind of nuanced things you can do about placement of Makeup Air systems, but generally speaking, neutralizing that pressure and keeping it from going negative in a humid climate is a big deal. So definitely works. You just need a dedicated system to dry.
Okay.
Looks like we got it right.
Thank you. I really appreciate that. We sometimes get a little bit of flack for a lot of us being in the Northeast. So thanks for joining in. But it is now 8 o'clock. Someone had, so I'm going to ask our panelists. I appreciate most of you for coming on. Do you have any last words or wisdom that you'd like to share with us? And then we will say thank you for joining us. We appreciate it. Thank you, NESEA, for agreeing to do this as a joint venture with us tonight. Thank you, Fine Home Building and Green Building Advisors. So to our panelists, we'll start with Kyle. Any last words or wisdom?
I think the big takeaway that I got from giving this presentation and doing some more research to further my knowledge in this, use your range hood. Like if you're cooking with an oven or your range top or a toaster, use your range hood. Capture those particles as much as you can. I think that's the easy takeaway and could make a huge difference for people in their health.
Thanks, Kyle. Ben?
So one of my favorite parting words from former BS and Beer was to try not to suck. Like, I think that's like a really important thing that we need to do in the industry. But I'm going to reverse that. In this case, we need to really try to suck the pollutants out of our kitchens. So let's pay attention to it.
Thanks, Ben. And last but not least, Ross.
Oh, man. Hopefully the takeaway for most people is that an ERV or HRV does not equate to makeup air, right? Balanced ventilation is not, does not, make the case for removing makeup air from our systems. We still need makeup air for our kitchen hood exhaust.
Yeah. So thank you, all of you, for spending actually an extra half an hour with us tonight on the BS and Beer Show and joining us and giving your expertise. We appreciate it. Thank you.
Thanks, everyone.
Thank you.
Thank you, everybody.